Donc, du coup, nous allons commencer. Je vais rapidement introduire le sujet et pourquoi, qu'est-ce qui nous mène ici, qu'est-ce qui nous mène là. Alors, nous sommes des étudiants de l'ESGI en 5e année dans la filière IW, Ingénierie du Web. Et dans le cadre de notre formation, on a organisé ce meet-up sur le thème le machine learning et ses applications pour vous présenter un peu ce sujet. On a choisi ce thème parce qu'on pensait qu'il était assez pertinent avec notre formation, qu'il était intéressant. Oh, alors, ok. Oui, donc du coup, je disais, nous avons choisi ce thème parce que il était pertinent, intéressant, qu'il était dans un domaine qui nous tient à cœur et on voulait en savoir
On
plus.
t'entend plus, Kenny, si jamais.
Je vois pas trop le chat. Si, c'est bon. Ok, non, c'était bon. C'est bon, vous m'entendez bien? Ok.
I'm sorry, we can't hear you, Kenny.
On m'entend pas ici, mais on m'entend normalement sur le Zoom. Sinon, ça fait répétition. C'est normal. Donc, du coup, je disais. Oui, donc. Ah oui, donc du coup, aujourd'hui, on va vous présenter on va vous présenter une réunion avec deux intervenants, donc Lohic et Léane, qui vont vous présenter du coup des sujets différents par rapport au machine learning. Alors, les deux conférenciers s'exprimeront en anglais et vous pouvez à tout moment poser des questions en français avec eux depuis le chat. Voilà. Je vais à présent laisser la parole à Liane, à Lohic plutôt, qui va commencer. Lohic, tu peux commencer.
D'accord. Je partage l'écran.
Nous, on va désactiver nos caméras et nos micros.
D'accord. So, hi everyone. I hope you can hear me. I am Lohic FOTIO, as you can see here, from the Politecnico of Torino, where I'm conducting my research, right? The context of the last year of my PhD. And I'm going to explore with you tonight some application of the machine learning techniques in the context of media quality assessment, right? So let's see, first of all, the main outline of this talk, right? Three main topics, right? I will first introduce you to visual quality assessments. Then we'll discuss how machine learning techniques are used in that context. And finally, I will give you a brief introduction to a topic that has attracted my attention during this last research year, right? So let's introduce the application. What we mean by image quality assessment or visual quality assessment in general? By visual quality assessment, we mean being able to evaluate, right, how much distortion is present in an image or in a video. Clearly, the more distortion there is, the lower will be the visual quality of the image. So, just a question for all the audience, right? And I would like you, please, to write your answer, right, in the chat. If you are asked, please try to follow me because this part is really important, and it's a sort of experiment that we will do in order to better understand the remaining part of the presentation. So please, I will kindly invite you to rate the visual quality of these images on the scale from 1 to 5, where 1 stands for very bad and 5 stands for excellent quality, right? If it's not clear, maybe I can repeat this also in French for our French speaker, if there is any. Donc, j'aimerais que vous évaluez la qualité de ces images sur une échelle de 1 à 5. C'est une évaluation subjective, hein, totalement subjective, sur une échelle de 1 à 5, ou sur laquelle un score de 1 voudrait dire la qualité est très mauvaise et 5 voudrait dire la qualité est excellente. Please try to write your answer on the chat, right, in an ordered manner. For instance, please, and write all the 4 answers, right, simultaneously so that we can collect them. Essayez d'écrire la réponse dans la chat, s'il vous plaît, en écrivant de manière ordonnée. C'est-à-dire, vous écrivez votre évaluation de la qualité des 4 images de façon ordonnée. Vous commencez par celle-ci, par celle en haut à gauche, et vous terminez par celle en bas à droite. Merci. Prenons un peu de temps pour le faire. There is no right answer. There is no wrong answer. Please, just give an assessment that is an evaluation that is your own perception, right, of the quality of that image. OK.
Alors, on a plusieurs réponses. On a Thomas qui a dit 3, 4, 3, 4.
OK.
Il y a Miyokichi qui dit 3, 3, 2, 4. Amand Drake, 80, qui dit 4, 3, 2, 4. Et Pokoki qui dit 3, 4, 3, 4 aussi.
Okay. D'accord. What is interesting is that you observe that different observers gave different opinions, right? In particular, let's focus on this image here. Can you see my mouse? I believe yes, right? Let's focus on this image here. If I am not wrong, 4 persons evaluated the quality, and you got 3 persons says that the quality is 2, and 1 person says that the quality is 3 for this image here. So at the end, having all these opinions, up to you, how do I proceed to get to evaluate to find out a single number as the visual quality? A possibility is just to take the mean or the average of all those opinions. Again, staying still on this image here, the opinions that we got was 2, 2, 3, and 2 again. Therefore, the quality of this image, right, the mean opinion score for this image is 2 plus 2 plus 2 plus 3 over 4. That will give us a number between 1 and 5, right? That number is called the mean opinion score, or the most of the image. Okay? Now, it's clear that we can show the image to people and they express the opinion. But this strategy is somewhat time-consuming. The question of interest for us is that can we design an algorithm that is able to predict, right, the mean of the opinion score for a given image? Okay, that is the main question we have. So basically, in the context of research, to get the quality of an image, what we do is that we invite people in a lab. We ask them to watch a given image or a given video. They express their opinion on the basis of this scale here, where 1 stands for bad, 2 stands for poor, 3 for fair, until 5 that stand for excellent. We average their opinion, and we get what we call the mean opinion score, the most, right? The mean opinion score represents the subjective quality of the image because it is given by subjects, by viewers. The most is a reliable estimation of the quality. But what is the inconvenience with the most? What is the disadvantage? Getting the most is time-consuming, but it's time-consuming because you need to invite person, convince them they should come in the laboratory and assess the quality of each image, right? And it is also expensive for the simple reason that you need to prepare a lab, to pay for the tools, okay? And but do you imagine that Netflix, for instance, can produce any video that Netflix produce? If they would like to assess the visual quality before uploading the video online, should they call many persons and ask them to look at the video and rate the quality? No. The answer, we need algorithms that should be able to take a video or an image and predict the visual quality, right? Without the need of calling person to perform the test. We need algorithms that should predict the most, right? The most, or the mean opinion score. From this, I want to make sure that everybody got the fact that the most is a reliable estimation of the quality of a video or an image, but it is time consuming and expensive to get it. Now, we need to design algorithms that can take and input an image and try to predict the most. What is the goal of those algorithms? Why are those algorithms important? As I said before, we need an algorithm that can be used to predict the quality without the need of inviting persons and asking them to watch the content, right? So the first skills of those algorithms is to use them to make sure that the person that will use the video that we are producing will experience good quality. On the other hand side, those algorithms are also useful for codec comparisons. Again, what is a codec first? A codec is any tools that you use every day for compressing a video or an image, right? Compression is useful. However, when you compress, you introduce artifacts. Look at this image here. What can you observe? You observe that the compression, right? By compressing this image, we introduce in the image some blocking, right? These blocks that you can see here, these squares that are perceptible from the image. This blocks somehow impair the quality of the image, and this is due to compression. Now, the point is, if I need to compare two codecs, right? How can I proceed? Which one is the best? The point, if I take two codecs and I use that to compress a given image, the codec that is the best one is the one that guarantees the highest quality, right? And to be able to know this codec guarantee the highest quality or this one, I need an algorithm I need an algorithm that is able to take the image and say, okay, the quality of this one is better. So let's use this codec instead of the other one. Is there any question so far? If there's a question, maybe you can write in the chat and Kenny can translate it to me. Is there any question? Okay, no question. Nice. So, our goal is to design algorithms that are able to take an image or a video and try to predict the visual quality of that image and try to predict the most. Why is this problem challenging? By the computer point of view, an image is simply a matrix of values where each value is a pixel. So what we are doing here is asking ourselves, is it possible just to give a matrix of value to a computer and ask the computer to predict the visual quality? How can the computer move from such a matrix of values to determine what will be the visual quality that a human will perceive? That is the question, right? Now, intuitively, you can say, since an image is just a matrix of data, I can take the original picture or the original image, okay, take the matrix associated to the original picture, take the matrix associated to the distorted picture, subtract them, and the difference between the pixel will give me information about the quality. Unfortunately, this naive subtraction is not really correlated with the quality. Why? Suppose that I simply add to each pixel here a constant. Let's say that to each pixel or to each value here, I just add 5. You will change the value of each pixel. But since you just added a constant, you are just making the image more brighter, right? You are not changing the quality. But if you then subtract from the new image, right? The image on which you add a constant, the original one, you will get a pixel difference. But this pixel difference is not an indication of quality. On the other hand side, what happens if I just rotate? If I just take, in this image, I just rotate, right? I just rotate an object in this image. I am changing the value of the pixel, but I am not changing the image quality. Just rotating an object in an image does not impact on the quality, right? So just subtracting pixel by pixel does not give an idea, does not really correlate, right, with the image quality. In this first part of my explanation, to tell you why the problem is challenging, I analyzed the subtraction between the original image and the distorted one. But in some applications, the original image or the original video is not even available. So you just have the distorted image, that you just have this matrix of value, and you would like to predict, but you would like to use a computer to predict the visual quality of the image. So the problem is even more challenging. Now, the machine learning approach, machine learning techniques are really suitable for this application here. That is for predicting the mean opinion score. Let's remind the problem. The problem is that of taking an input, is that of designing an algorithm that can take in input an image and try to figure out or to predict the mean opinion score, the MOS. That is the visual quality. To better understand why machine learning algorithms are suitable for this task, it is important to recall the difference between, right, the traditional programming paradigm and the machine learning-based paradigm. In particular, in the traditional programming approach, what you do is that you have a problem, you write a set of instructions, and after writing the set of instructions, you just use some examples to check whether the set of instructions that you wrote for solving the problem are exhaustive. But the machine learning paradigm instead do what? We do not end with example. We start with examples. We collect some examples that we show to the computer, as you already know. And then from those examples, the computer learns the instruction. We are not the ones that write the instruction. This is perfect for our case, right? Since the machine learning paradigm is the one that, by adopting the machine learning paradigm, we are asking basically the computer to learn the instruction. This is good for us because, in fact, we are asking ourselves, what are the instructions that the computer should implement in order to move from an array of data that represent an image to the visual quality? So what do we do in the context of visual quality prediction? In the context of visual quality prediction, there are two main approaches when we decide to use machine learning or artificial intelligence-based approaches. There is the so-called machine learning-based models, okay, and also the deep learning-based one. Let's start from the machine learning-based models. In the case of machine learning-based models, we take a video or an image, we manually extract the characteristics or the features that are expected to determine the visual quality of the image. For instance, the texture, the quantity of details in the image can impact on the perception of its visual quality. Why? The more there are details in an image, the more difficult it is to perceive the distortion. On the other hand side, the luminance, the brighter an image is, right, the more difficult it is to see the distortion. Therefore, one can extract a number of characteristics that are called features, okay, that are expected to characterize the visual quality of the image, and then try to map this characteristic, right, to the MOS scale. From this characteristic, each of these characteristics is evaluated on a range from, let's say, from 0 to 100, or on something. We assign a numeric value, right, to all these characteristics, and ask ourselves, given those characteristics, what will be the mean opinion score? What will be the MOS? In the case of a video, for instance, except these are some examples, right? In the case of the video, we also care about the temporal direction of the video. You know, a video is simply a sequence of images. And in particular, in the case of a video, something that is also important, something that impacts on the quality perception is the quantity of motion of the object in that video. Researchers has developed a lot of algorithm for measuring, right, for extracting an estimation of how much objects are moving inside a given video, right? The more the content is dynamic, right, lower is the perception of artifacts. Now, typically, what do we do for getting a machine learning based model for image visual quality assessment? We prepare a data set with a lot of images. We extract the features. We show those images to people. So we do what I asked you to do at the beginning of the talk, right? Where I asked you to evaluate. Each of you gave his own opinion regarding the quality. Then we average the opinion to get, right, the mean opinion score. So for each image, we have both the features of that image, and we also have the mean of the opinion of the observers, right? This means opinion score are called labels. Now, all this is called these are our examples. These are the examples we would like to present to the computer and ask the computer to learn how to move from the feature to the mean opinion score. This data set is then divided in two parts: a part, the training set, and the test set, right? On which we will the training set, we use it for training, and then test the performance of our model on the test set, right? Now, what is the point? This is just, right, I mean, when we say learning process, when we say, okay, we are going to train the model, what are we basically doing? We have a set of features, and a set of features that characterize the quality of the image. Our question is how to move from the features to the mean opinion score, right? By the word learning, when we say that the computer is learning, the computer is just basically finding the instruction to be applied on the features to reach an estimation of the mean opinion score, right? And those instructions is summarized into a function that we will call here f, right? The computer tries to find out a function f that should be applied on the image characteristic to reach an estimation of the MOS. Therefore, when we do f apply to all the features that we extracted from the image, this gave us what? An estimation of the MOS. If we do that estimation of the MOS minus the actual MOS or minus the actual visual quality of the image, we get the prediction error, right? What we are doing here is therefore taking the average of the prediction error. During the learning process, or when we say that we are training the model, right, to recognize how to assess quality, what we are doing is to we are asking the computer to determine the function f such that the average prediction error is minimized, right? Obviously, this function f typically depends on some parameters called weight, right, in research, that are to be determined. The structure of the function f determine the machine learning algorithm that you choose, right? Different machine learning algorithms let's say, for instance, that if you use a regression model, the function f will have a certain form. You use a neural network and so on, the function f will have a certain form. So the structure of the function f depends on the machine learning algorithm that you are using. Now, to provide a concrete example of the application of machine learning, right, in visual quality assessment, most of you probably has already subscribed to Netflix. And Netflix used the so-called the VMAF algorithm to assess the visual quality of its contents before uploading them online, right? So when they produce a content, they use the algorithm called the VMAF to assess the content. This is an algorithm developed also in collaboration with one of your famous institutes in France, in collaboration with Patrick Lecalé, right? I don't know whether you know him, but he's really famous in our research field and so on. So, and the VMAF is a machine learning based algorithm, right? And it is designed on relying on the so-called support vector regression model. That is one of the well-known machine learning techniques. You can this scatter plot here is basically showing the correlation, right, between the quality as predicted as VMAF does with the mean opinion score. You can see the VMAF score right? The range of VMAF score is typically from 0 to 100. And the VMAF, when the algorithm output a high value, also the mean opinion score is high. There is a good correlation, right? Now, if you remember, I told you that there is, in the context of visual quality assessment, there are two approaches, right? When it comes to the deployment of machine learning techniques, we can basically rely simply on what we call machine learning-based model or move to deep learning-based model. What is the main difference? In the context of machine learning-based model, I told you that features are manually extracted, right, by the person that designed the model. But in the when one deployed a deep learning-based model, the architecture of the model, it's designed in such a way that the model itself should extract the features that are important to characterize the visual quality of the image, right? On this slide, you see what the typical architecture of a deep convolutional neural network, okay, where two parts here are pointed out. In particular, the first part, that is called the convolutional part, is used to extract the characteristics of the image that contribute to determine its visual quality. And the second part, called the regression, or is the part that once when the feature has been extracted, map them to the MOS scale, okay, and reach the prediction of the MOS. Now, what is according to what we just said, you understand that the best advantage of using deep learning-based model is that prior knowledge of the topic is not required. The model itself figures out the features that are important for predicting the visual quality of the image. Why? For the machine learning, you need to have, if you want to use a machine learning-based model, you need to extract the feature by yourself, and therefore some prior knowledge of the topic is required. Another important aspect, or another advantage of using deep learning-based model is basically that they have empirically shown to yield better accuracy. But obviously, there are some disadvantages. To train a deep learning-based model, you need a really large training set. And as you understood since the beginning, it is really expensive to get the training set, because to get the training set, to get a large training set, you need to ask a lot of people to evaluate a lot of images, and this is time consuming. And I can tell you that nobody is willing to evaluate more than 300 images. So it's really hard to get large training set in the context of image of a video quality assessment, right? On the other hand side, deep learning-based models are also difficult to be implemented in the context of visual quality assessment, not only in the context of visual quality assessment, because they are computationally demanding. What do I mean by that? It takes a significant amount of time to train, right, a deep learning-based model. We are talking about many weeks, many months in some cases. Now, okay, obviously, these issues those issues have not prevented the deployment of deep learning-based model, however, in the context of visual quality assessment, because people have proposed a number of strategies to overcome the issue. In particular, you have the strategy of data augmentation. That is, it's known by any machine learning practitioner, right? It's not something related to visual quality assessment. So data augmentation consists in augmenting the training set to reach a large training set that is necessary for training a deep learning-based model, right? How do we do that? You remember that in the training set, we need an image with the related MOS. If I take the image and I just perform some basic transformation that are expected not to change the MOS, I can create new images to put in the data set, in the training set. So we take an image, we rotate some element in the image, or we rotate we change the motion of some object in the video. By doing this basic transformation, we are not changing the quality. So we can create other items to be inserted in the training set. These strategies are called determination. Another strategy to overcome the issue posed by deep learning-based model is the so-called transfer learning. What is transfer learning? You basically take a model that was trained for another task. Let's say, for instance, image recognition or scene classification, anything you want, and basically continue the training process of that neural network on a visual quality assessment data set, right? You modify a bit the weight or the parameters of the model to transform it into a new model that can be useful for image or video quality prediction, even if the model was originally designed for other tasks. This is called transfer learning. Is there any questions so far? Okay. So to conclude the presentation, let me share with you give you some insight regarding what has been my research topic in the last year. In particular, talking here, I'm going to talk here about the so-called AI-based observers. That is an idea that I introduced myself in the research community, right? So I propose, right, for the first time in the context of my research, to use neural network to mimic observers in terms of quality perception. So far, I told you that we are interested in training models for predicting the mean opinion score. But at a certain point, I say, no, let's try to train a model let's try to train a neural network that can replace an observer. Okay? So, for instance, if I go back to the experiments I asked you to do at the beginning, you can see that different viewers gave different opinion. Therefore, we can say, okay, if we ask Peter to evaluate the quality of a given image, he will express his opinion. We ask Alice to evaluate the quality, he will express his opinion. Therefore, what can we do? We can simply try to train a neural network that can replace Alice, and then train another network that can replace Peter, right? When those neural networks are trained, when they receive an image in input, they try to predict the opinion, right? The quality that Alice will have given, or the one that Peter will have given. We train one neural network for one observer. And this neural network is called an artificial intelligence-based observer because he's acting like an observer, but this neural network is just equipped with artificial intelligence. What is the advantage of using the artificial intelligence-based observer with respect to the traditional approach? If you have many artificial intelligence-based observer, when you produce a video or an image, you can use the artificial intelligence-based observer to automatically get many opinions and see whether there are some observers that like or dislike the quality, the visual quality of the content that you just produced, right? So on the other hand side, if you have a neural network that can replace an observer, since this is automatic, you can evaluate as many possible images as you like, or many possible videos, the quality of many possible videos as you like with that AI observer, and then analyze what are the characteristics of the video or the image that make an observer choose an opinion instead of another. So the deployment of the AI observer also gives the possibility to better understand the peculiarities of human vision system. So in practice, how do we train the AI observer? Let me make this a bit. I'm not sure whether you can see, but what we are doing here to train the AI observer. Let's say I want to train the AI observer that can mimic Alice. I just invite Alice in a subjective, in a laboratory, right? I show some images to Alice. She expressed her opinion, right? And then from this data, I can train a model that will later replace Alice. This model we call the AI observer of Alice. I can do the same for Peter, and I get the AI observer of Peter, right? So this is a strategy we use. In this case, we are extracting the feature. We are taking the image, we are extracting the feature and learning how to map the feature to the Alice votes, or also to the Peter opinions and so on. So we are adopting a machine learning based perspective. We can also do the same, so we can train still neural networks that mimic single observers in terms of quality perception, but by adopting a deep learning based perspective. Why should we do that? In the case of machine learning, we are using the same features for all observers, but again, observers perceive quality differently. Maybe Peter will look at the image and something will not be annoying for Peter. Why that same thing will be annoying for Alice? Therefore, we need some algorithm that is able to figure out what are the optimal features for each observer. And by adopting a deep learning perspective, since the computer automatically extracts the feature, we expect that it extracts the right feature for each observer. But when moving from machine learning to deep learning, again, we still have the issue of the lack of large-scale dataset. We need large-scale dataset. How can we proceed? An idea that we propose, I and my colleagues, during in the context of our research, is that of creating some synthetic data, right? In particular, we take an image, we compress it using 5 different level of JPEG compression, and we label it as we assume a human will do without doing a subjective test. Using this strategy, we created a large synthetically generated training set, and we use it to train a deep neural network or a deep model that we call the JPEG ResNet 50. Now, this JPEG ResNet 50 is able to classify or to determine what is the level of JPEG compression of a given image. Having these neural networks that is yet able to figure out some features concerning the quality perception, we can continue its training, right, on the data collected, let's say, for instance, from Alice, without any more using the feature, right, and start from the feature of the JPEG ResNet, and we progressively transform them into features that characterize the Alice perception of quality. At the end of this training process, we reach a deep neural network-based model that can replace Alice in terms of quality perception. That means that if I give as input to that deep neural network an image, that deep neural network is expected to predict the opinion that Alice will have given after watching that image automatically. Now, I will quickly show you some results that I got with my colleagues in the context of the research. Here, you can see we evaluated, right? We used the AI observer. We asked the AI observer to evaluate the quality, right, of some videos, and we also asked the actual observer to evaluate the quality. And later, we compare the mean opinion score of the artificial intelligence-based observer to that of the actual observer. You see, there is a good correlation, right? When the artificial intelligence observer believe that the quality is high, also the actual observer do the same. The same happen also when the AI observer believe the quality is low, the actual observer also do the same, right? There is high correlation actually. Here you can see the so-called confusion matrix of the JPEG ResNet, right? And in particular, you see that most of the time, when we use the JPEG ResNet to classify 200,000 images, we are basically asking the JPEG ResNet to recognize the level of JPEG compression. And if you see, most of the time, most of the images stay on the diagonal of this matrix, and basically says that the predicted class of JPEG compression anytime were equal to the actual class of JPEG compression. Finally, when you have the AI observer, what you can do is that you can ask them to express their opinion on for a given image. I mean, I'm saying asking them, but in fact, we are not asking them. We are just using them, right? We just give an image in input, and they are expected to provide the opinion. So we take a given image and we degrade its quality using different level of JPEG compression. You can easily see that by moving, this is very bad quality, and by moving from top to down, the quality is increasing visually. So if we use our AI observer, our artificial intelligence-based observer, and ask them to express their opinion, if we ask to our AI observer to express their opinion on these images here, what happened? You see that for this image, almost all the AI observer deems the quality as bad, right? The image below, they deem the quality as poor, and so on. And as you are moving down, for instance, in the last case, when the quality it's relatively high, most of the AI observers deem the quality as good and excellent, right? While few of them believe that the quality is fair. So as the quality is increasing, the opinion are moving to the right, as expected. This result basically somehow show that the AI, the artificial intelligence-based observer, are behaving like actual observers, right? So these are some reference, right? In particular, the first one is a paper related to the VMAF, as I told you. The second one is a conference paper where you can have a preliminary. It's a conference paper from my authored by some colleague of mine, including I am one of the authors also, and it was presented at the HY conference, right, in America. So you can have a look on it to have a rough introduction to AI observers and so on. And then there are also two journals paper that are submitted for publication to the ACM transaction and IEEE transaction on image processing. I thank you for your attention. I don't know actually whether the questions are to be answered right now or at the end of after the second speaker, but I am here and ready for any question. Your question the question can be formulated in English or French. I don't mind.
Thanks a lot. We have some questions for you. Martin, can you say the question, please?
So we got a question. Can we measure visual quality assessment to detect if there is a deepfake photo?
Actually, yeah, it is something that is surely possible, but so far it's an application that has not been yet considered, to the best of my knowledge.
Thank you. And we got the last one. And what from AXO is what does VMAF stand for?
VMAF, it's actually it's the VMAF. Sorry, I'm coming. Oops, sorry. Oops. Oh, okay. By the way, it is video multi-method. Sorry, the right thing is, I believe it's video multi-method. No, sorry. It's video. It's an idea come from. I mean, video multi-method fusion. No, I am confused. But by the way, the idea is it's a mixture of many methods, right, for getting a better method. And I think you can see it online on Google or anything. It's very famous. I'm just missing the right traduction right now, but it is something like video multi-fusion assessment, video multi-method assessment fusion, or it's quite close to that. But the right The right acronym, I am forgetting a bit right now. Sorry. But I think something like video multi-assessment, multi-method assessment fusion or something like that. Quite close. Sorry.
Okay, thank you. That's all.
Any other question?
No. Thanks a lot, Lohic, for this presentation. Thanks a lot. Yes, we're gonna go with the next.
Okay, fine.
Next
So I
one.
will share my screen and let the next speaker to proceed. Obviously, I'm still here. So if there's any other question, I will be happy to answer. Thank you.
So thank you for having me. Thank you, Mr. Lohic FOTIO. So my name is Thanh-Lan. I'm actually not a expertise in machine learning. I work as an apprenticeship in Allianz Investment Management. And our job is actually asset liability management. But one of our mission is to apply machine learning to predict the economic scenario relating to the market. So today I'm going to introduce the application of machine learning in the finance world. And the machine learning algorithm is a build model based on the sample data and to make prediction and decision without explicitly programmed to do so. So it falls into two main categories: supervised learning and unsupervised learning. The main difference between these two categories is the supervised learning require label data. So like the presentation of Mr. Lohic FOTIO is all the image that have to be labeled first. That is the first step. So it's also a one method of supervised learning. Okay, depending on the purpose, the supervised machine learning. I'm sorry for that. So based on the method, we have the supervised learning, which can fall into two purpose: the classification and the regression. As you can see in the first picture, we have the picture of two classes. And what we want in the machine learning to do is draw a circle to tell you that this circle represents one class that we are looking for. So, of course, we're going to have the green one, which is true one of the correct classification. But then we also have the red one of the false classification, but we talk about that later. The second application of supervised learning is regression. It tells you that the dependency between the two or more variables, we have a number of independent variables, and the machine learning will draw out the relationship with the dependent variables. Okay, and the last one we have unsupervised learning. Basically, the data is raw and not pre-labeled, but then we want to speak something intelligent about this raw data. So machine learning provides a method to split it into different clusters, and the number of the cluster that we are expected to have, in this case 3. But today our main focus will be the supervised learning. So there's two common example of the case study of supervised machine learning. We have the classification problem, and also we have the regression. So if, let's say, our purpose is to classify data, we're going to ask in our example, so within the bank, if you deal with the credit card client, the bank wants to know that whether or not this client or how many clients that are fall into the default category or not default category. So default here means that the ability that this client is not be able to repay their debt or their credit card debt. So the banks want information and machine learning to tell them that to predict that whether or not this existing client is likely to be default or not. Okay. The second case, they want to categorize fraudulent transaction, the same approach with the supervised machine learning. But then, if you want to ask the other question about regarding regression, it would likely to be how to determine a probability of default and how to determine the probability of fraud risk. And the difference is between classification and regression is that machine learning works with when it works with finite class of outcome, it will be classification. But then when you turn to continuous variables, it will be regression. So why do we need machine learning? So instead of traditional method, here is our question. So given the information on the right, we have three gentlemen here, and how to predict whether or not these clients are able to pay back their credit card debt. So regarding his income, we also collect data about his work experience, their level of asset, the year of education, the monthly bills, and the repayment made monthly. So given the traditional approach, now here we set a number of rules, and we have all the class pre-labeled for historical client. From this, we also have other feature. So feature here is exactly the income, work experience, assets, and monthly payment, etc. The difference between this machine learning and the one with Mr. Lohic FOTIO is that we don't have to extract the feature, but all this data is likely to come from historical data. So we all, the bank all collect the income, their work experience, the level of their asset, their monthly bills and payment made without any action of feature extraction. Okay, but still we need to process the data like missing value and duplicate value and outliners, etc. So the traditional method, their approach is that they apply a set of rules that say, oh, if their income is 3 times larger than their average monthly credit card debt, it's likely for this client to pay back the debt, right? On the other hand, it's very naive to think that if their work experience perceived 5 years, they're likely to pay up the debt, or etc. Then the traditional method made up these arbitrary rules. They tested it on the historical data, and they keep updating the rules until they feel satisfied with this rule. And that is when they apply this rule to new data to predict whether or not these three gentlemen is likely to be default or not. Okay. But then taking the machine learning approach is pretty similar. But instead of creating arbitrary rules, they apply the function like the machine learning algorithm. We can consider it function. It's the same as in the slide of Mr. FOTIO. But then we also collect historical data. We have all the label, which is also the class. We have all the features. We put these data into our machine learning algorithm with the training and testing and sometimes validation in order to figure out all the parameters of this function. And from this function, we apply new data and we can predict the future value of other clients or existing clients. And also from a number of machine learning algorithms, we don't only have one algorithm. We have a number here is m function, and from this we can tell after we validate this function, this algorithm, we can tell whether or not which function is the optimal one. And it's not possible in the traditional approach. You can possibly know that if your rules is optimal or not. Okay. So the traditional method, as I said before, it includes bias judgment. So there's will be low accuracy. It's not possible to parameterize or optimize. Why the machine learning act as a function? It has the higher accuracy, higher speed of computation, and is parameterizable and optimizable. So here I take an example, actually a research paper from Xian Hulian, the comparison of data mining techniques for the probability of default of credit card clients. We can see here the data collect is 30,000, but in these 30,000 clients, we have 6,600 people who's actually default. So this is historical data. Our dependent variables is binary variables, and we set it if the client is default, we set it to 0, and if the client is made his payment, we set it to 1. We also have other independent variables like the given credit, gender, education, age, history of past payment, etc. So in practice, the first thing when we do before we apply the machine learning algorithm is that we take a look and read and understand our data. Here, our first problem is that only 22% of the people among 30,000 clients are actually default. So it means that there is difference between a majority class and a minority class. So the machine learning algorithm can produce output which is biased to the majority class. And is it common that the minority class is usually the focus of our study? So in here, we want to find the people that is likely to be default. And if the data, the input data is imbalanced, that means that the machine learning output can be biased toward the majority, which is the one that is not default. Okay, so there's actually two main types of solution here, which is undersampling and oversampling. So the undersampling, the idea is it takes the majority and randomly or stratify randomly delete the data in order to have the same level, same quantity of data with the majority. And in oversampling also, they try to duplicate or synthetic create new data. It actually relating to Mr. FOTIO presentation, it actually synthetic create new data from the one that is minority, and in order to have the same level of data for both majority and minority. Okay. So after we have balanced data, we turn to machine learning algorithm. Here, there's a number of machine learning algorithm we like to try. Then I will explain briefly about these three first machine learning algorithm. First one we have is logistic regression. This is a linear algorithm that is very common use in finance, particularly in credit rating or credit or measuring the probability of default. Here, our case is that we try to model the probability of not default because we set the default is to be 0 and the one who is not default is 1. If you see in the graph, we have the blue square here is the one that made their payment in the past, and they are not default, okay? But then the red dot represent the one is default the payment. They are not, they don't have the ability to pay their debt. And what logistic regression offer is that it creates a green line here. So you can see it's ranging from 0 to 1, and it represents the probability of not default. And the green line is actually training from this data, the historical data. So if you can see, if the ratio, the monthly income / average monthly credit card is larger than 5, is the green line is likely to be close to 1. So it's 100% of probability of not default, or 0% of probability of default. So in economics sense, we will say that if you have income that is more than 5 times of the monthly credit card payment, you are likely 100% to pay up all the debt. But then if you have this ratio less than 1, it's actually maybe like almost 100% that likely for this client to be default on their payment. Okay. So another method, another algorithm is decision tree, which is also very common use in the world of finance and machine learning. It represents a tree and apply a series of tests that are conducted against the input. So each test is a question. So here the first question is that whether or not income over the average monthly credit card debt is larger than 3. And the answer represents the age of the response, yes or no. And the outcome of that is represent the leaf node, is not default or default. Okay, so here we have a very simple decision tree here. So let's say our data have only 2 questions. And then after you ask these 2 questions, you apply the new data and you ask a new client that who has a income smaller than 3 times their credit card debt, and also they have less than 4 years of experience, is likely to be default. So we are trying to find the person who is likely to be default, and we apply these 2 questions. Okay. Talking about another algorithm, so we actually have a random forest, which is a combination of the randomly created decision tree. We have different decision tree. We have different order of feature that we want to test also. Or we can also have different data set that we want to apply this test to. So each decision tree have maybe they have different data that they are training on, or maybe they have different set of tests that they want to test. Okay. And the result of random forest is by averaging or majority voting of these the collection of these decision tree to have the final result. So we should consider both the advantage and the disadvantage of each algorithm. So logistic regression is easy to use and perform well on simple data, especially when they are linear separable. We have also decision tree, which is easier to interpret and take less effort for data pre-processing. Also, it can handle non-linear relationship, which is not possible by logistic regression. And moving on to random forest, it also can handle non-linear relationship, can maintain accuracy, and actually reduce variance from the single decision tree, because it combines a selection or a large number of and also randomly created decision tree. Okay, about the Also, the disadvantage of each, we can see each algorithm have its disadvantage. So after we have this machine learning algorithm applied to our data, not the after, but the thing is to validate the machine learning algorithm. Before we apply this algorithm, we split our data into two sets, training set and test set. And here, there are actually a number of course validation method. We choose here a k-fold course validation method by splitting a training set into equally false, k equally false, and then we train our model into the rest k minus 1 false before testing on that chosen false. And we repeat this process 5 times in this example before having a final evaluation. So for the performance of these tests, so splitting the data is to train and test the model, but then when it comes to formula, we apply these 4 formula to see how the algorithm works and perform. So the accuracy here is all the true answer, the true positive, the one that you predict, which is correctly classified, divided for all sample that we have. So in here, in the chart here, the graph here, sorry, we can see that I have 2 squares, which is represent 2 class, and we want our algorithm to draw a circle representing a certain class. So let's say I want to draw a circle representing this class, and then I realized that a part of my of the algorithm prediction is correctly classified, which is this area, but the one here is false positive, which is wrongly classified of the one I want to predict. Okay, so the precision ratio tells you that among the one that the model predicts, this one is true. So how much of this prediction value is correctly classified? We also have the recall ratio, which tells you that in the class that I want to predict, how much of it I capture in our models prediction. Okay, and this one can be represented like in this image. And the F1 score is actually the weighted average of these 2 ratio that tells you the both characteristic of this performance. And the result of when we apply in our data is this. As you can see, the test accuracy, precision, and recall is not very high. And also the F1 score, which is weighted average of test precision and test recall. But we can figure it out which algorithm have best performance here. The CatBoost have the highest accuracy, but actually have the not as high the F1 score. So in here, depending on your characteristic, your category, you want to highlight the F1 score because you want to capture the right class, but also you don't want to capture the wrong one too much. So in here, all the logistic, the gradient boosting method, and the support vector machine classifier have the highest F1 score. Is likely to be optimal, but then we consider the fitting times. So we have the logistic is the fastest, and gradient boosting also have the high speed of computation. So we consider these 2 the optimal algorithm. So in conclusion, I want to state out that we have to be careful when we work with imbalanced data. This is highly likely the case when we deal with the problem in finance, in particular, in also insurance. And the rules of thumb is to implement a variety of algorithms, not just one. And we have to consider the advantage and disadvantage of this algorithm. However, we have to note that understanding the problem, and when we select the data, the relevant variables is much more important than selecting the algorithm. So if you understand your problem and you reach out, you capture, you collect the right variables, it's more likely that you would have a very just simple algorithm. Don't need to be sophisticated all the time, but then we have to very clearly understand which variables have the direct impact to our prediction. So if we collect that data, we are able to collect that, so we'll have very simple algorithm. And also choosing the algorithm with the highest performance have to consider both precision and recall ratio. So thank you. If you have any problems, any questions, sorry, you can ask now.
Thanks a lot for this presentation. Yes, we have saw some question. Martin, can you say it, please?
Yes, Miss Laurent. So,
I will let Duy-Dung ask to Jan, I think.
Okay.
The answer is yes. We can definitely add new data to continuously train our models. So we can run our model at any times, and the more you have recent data, I think in finance, the more relevant you have on this outcome. So taking the situation of COVID epidemic, if you have recent data, it's likely to be more precise to predict the near future than the data from 10 years ago. So we can add continuous variables, the recent one, to our model as well.
Okay. The second question. Since unexpected events like yielding in an unexpected geographical location, so maybe really fundamental for fraud detection. So how do you account for that in your model?
Yeah, it's actually a very good question, because when we train our models, we are supposed to highlight the outliners, because it's likely to have the outliner, which is an unexpected event and unexpected relationship, an abnormal relationship between these variables to the one we predicted. But then it just consider an one-off case. If you consider this an usual events, you have to reflect in your models. But then if you take into account also the unexpected model, is likely to be overfit for your test set. So if you perform well in your training data, you input the unexpected event in your training data, but then that unexpected event is not reflected anywhere in the test data. So you can see the performance when you apply to the test is very low. It means that it overfit our model. So we're gonna reflect most of the case when we train the data, and sometimes we have to get rid of the outliners. So do you have any other question?
No, it was the last question, I think.
Thanks a lot for this presentation. We very appreciate what you're doing. Yes, thank you for your email. Just for saying, we have put the email of the other one in the chat. If you want to ask their question, you can contact them. Thank you.
Okay, thank you very much.
Okay, Kenny, I am just wondering, can you hear me?
Yes.
Yes, we can.
Can the audience still hear me, or?
Yes, everyone hear you.
Yeah, sure. Yeah, on the presentation, you can also share my email to the participants in case they have any further questions, and they could just they feel free to write to contact me so that I can reply. And also regarding the last question regarding the VMAF, as I said before, the right signification of the acronym, it's a video multi-method assessment fusion, right? And as I said before, the point is that this was the starting point at which people really start to trust machine learning, let's say, machine learning methods applied to visual quality assessment, right? But I will have to say that despite VMAF that is again visual video multi-method fusion assessment, it's called. Despite it's a really good algorithm, and it is actually it is showing state of the art performance. Most of the time, machine learning techniques, are deemed not, not really, sometimes not suitable, just because as my let's say the co-speaker said, you need really to structure the data set in such a way that you make sure that you are not overfitting the training set. And the question of overfitting, it's something that is really it's really present. It strongly affects machine learning based model for visual quality assessment, and this make the visual quality machine learning based model less trustable, let's say it like this, in the context of image quality assessment. But this situation is progressively changing because of the success of VMAF and many other strategies that are being investigated. Okay, just wanted to make this clear. I don't know whether the participant have any other question regarding what we said. Is there any other question?
Non, je pense que c'était la dernière question, Loïc.
D'accord.
Merci.
Merci.
Donc, en tout cas, merci à tous d'avoir participé à ce live. J'espère que ça a été intéressant pour vous, que ça vous a quand même appris des choses. Donc, je vous souhaite une bonne soirée. Et à très bientôt. Au revoir.
Thank you very much.
Au revoir,
Bye.
merci pour tout, bonne soirée.
Bye.